Hello everyone, welcome to Homework Help. If you find the videos useful, please subscribe to the channel. So in this video, we'll solve this problem using the concepts of derivatives. So as per the problem, the velocity of a car is given by v at t equals 120 times 1 minus 0.85 to the power t. And graph the function and describe the acceleration of the car. So we are given this the velocity function v at t, and we have to graph this function. Now in this function, the variable t represents time, and we know that time cannot be negative. So the domain for this function is t is greater than or equal to 0. Now we can analyze the discontinuities in this function. Now this velocity function is an exponential function, and we know that an exponential function has no holes or vertical asymptote. But an exponential function has a horizontal asymptote, and we can find the horizontal asymptote in this function by applying the limit t approaches infinity. Now in this given function, the term 0.85 to the power t decreases in value as we keep increasing the t value. So there's something you can check in your calculator. So as t increases, the value of this term 0.85 to the power t decreases. So as t approaches infinity, a very big number, so 0.85 to the power t approaches 0. So when we apply the limit, so 0.85 to the power infinity is 0. And 1 minus 0 is equal to 1, and 120 times 1 is 1. So that means the horizontal asymptote is at v equals 120. Now we should find whether the curve approaches this horizontal asymptote from above or below. Now since t is greater than or equal to 0, we do not have to do the analysis for the t-axis on the left side. So we'll just analyze the limit that t approaches a big positive number. So we can use 100. So we can apply the limit. So 0.85 to the power 100 is equal to 0.000, and then we subtract 1 from it. So I got 0.999. So 120 and this value 120 times 0.999 will give us a value that's less than 120. Now we want to analyze this value with respect to 120 because the horizontal asymptote exists as 120. And since this value will be less than 120, that means the curve approaches horizontal asymptote from below. So this is the end behavior of the curve on the right side of the t-axis. Now we can find the intercepts for this function. So we can start with the t-intercept. And for the t-intercept, we can sub in the v value as 0 and then solve for t. Now we can divide both sides by 120. So we get 0. Now we can move the 0.85 to the power t to the left side of the equation, and this term will become positive. Now the t value will be equal to 0 because 0.85 to the power t is equal to 1 for t equals 0. So any base to the power 0 is equal to 1. So the t-intercept for this function is, now we can find the v-intercept. So for v-intercept, we should sub in t as 0. So 0.85 to the power 0 is equal to 1. And 1 minus 1 is equal to 0, and 120 times 0 is equal to 0. So the v-intercept is, so now we are done with the analysis for the intercepts. So the next step is to find the critical points for this function. And critical points are points at which the derivative of the function is equal to 0 or undefined. So we have to find the derivative of this v at t function. Now in this given v function, so 120 is the coefficient of this function, so it will stay as it is. And in the parentheses, the derivative of 1 is 0. And for this exponential term 0.85 to the power t, the derivative is the term itself times the ln of the base times the derivative of the exponent of the exponential term, and the exponent is t and the derivative of t is 1. Now we can simplify this expression. So in the parentheses, 0 goes away, and ln 0.85 times 1 is just ln 0.85. Now we can evaluate ln 0.85, which is equal to negative 0.1625. So that will make this exponential term positive because two negative terms when multiplied become a positive term. Now we can multiply 0.1625 by 120. So I got 19.5. Now this will the first derivative is another exponential function, and there are no t values that will make the first derivative equal to 0 or undefined. So that means this velocity function has no critical point. Now we can check whether this function is increasing or decreasing over the domain t greater than or equal to 0. Now for all t values, this first derivative will be greater than 0 because no t value will make 0.85 to the power t in negative term. So that means our conclusion will be so the function v at t is increasing for all t values. So now we are done with the analysis for the first derivative. Now we can analyze the second derivative of this function and do the inflection point analysis. So we can find the inflection points for the function v at t, and for that we need the second derivative of the function v at t. So for that we'll have to find the derivative of the first derivative. Now in the first derivative 19.5 is the coefficient of the term, so it will stay as it is. And for the exponential term 0.85 to the power t, the derivative will be the exponential term itself times the ln of the base times the derivative of the exponent, and the exponent is t, so its derivative is 1. Now we can simplify this expression. So ln of 0.85 times 1 is just ln of 0.85, and we can multiply 19.5 by ln of 0.85. So I got negative 3.17 times the exponential term. So this is the expression for the second derivative. Now no t value will make the second derivative equal to 0 or undefined. So that means this velocity function has no inflection point. Now we can check whether the function will concave up or concave down over the interval t is greater than or equal to 0. Now for all t values, so 0.85 to the power t will give us a positive term, and if we multiply that by the negative 3.17, we'll get a negative value for the second derivative for all t values. And we know that if the second derivative is less than 0, that means the function is concave down. So for this function v at t, we can conclude so for all t values, the function will be concave down. So now we are done with the analysis for the function v at t, and now we can use all of these results to sketch the function. So that's the t-axis. The vertical axis is the v-axis. So let's start with the asymptote. So in this function, we have a horizontal asymptote at 120. So let's assume this point is 120. And the t and the v intercept are the same, the origin. Now we also figured out that the curve approaches the horizontal asymptote from below on the right side. So the end behavior will be like this. And the curve is increasing for all t values and it's concave down for all t values. So that means we can show the sketch like this. So as we go from left to right, the v values are increasing, so the function is increasing and it's concave down. So this should be the graph of this function v at t. Now we can answer the second part, describe the acceleration. Now the acceleration of the car is equal to the slope of the vt graph. So in this case, we can see the VT graph is increasing. So that means any tangent that we draw to this VT graph will have a positive slope. So that's why the acceleration of the car is positive throughout the curve. So that's our first observation. Now, as the time increases, the velocity curve approaches the horizontal asymptote and it becomes flat. So it means the acceleration gradually approaches zero on the right side. So that's our second observation. So as t approaches infinity, so the acceleration approaches zero because the curve becomes flat. So that's our second observation. So these are the steps you have to keep in mind to solve a problem like this one. So I hope you'll find this video useful. Please share it, like it and subscribe to Homework Help. Thank you very much and have a nice day. Bye.